So flip-flops are something called a bistable multivibrator. Okay, so there are several types of multivibrator. The multivibrator is something that only has two states, and so a monostable is stable in one of those states. So let's say, for example, a good analogy with a multivibrator is something like, a monostable multivibrator would be a pole standing up on its end. It'll be stable for a little while, but if you give it a nudge, it'll fall flat. Or sorry, if you leave it, it'll fall flat. You can stand it back up again, and it'll stand up for a little while and then fall back again. Okay. So a monostable is stable in one state. A bistable, you can kind of think of it as being a bit like a coin. Okay. If I flip the coin over, it'll land. Let's say it was heads up. If I flip it over to tails up, it'll stay that way until I flip it again. Okay. And if I flip it again, it'll flip back to heads and stay that way until I flip it again. Okay. So it'll stay in either of the two states until it's disturbed. Okay? And then there is the final type of vibrator called an astable. Okay? Now an astable means it's not stable. And what it will do is it will flip from one state to the next on its own. And it will do it as fast as it can possibly do it. Well, you can tell it or control how fast it does that. Now, a good way to show these kind of states is in what's called a timing diagram. So a monostable would look like this, say. So it's got a low state, and then there is a disturbance here. I give it a nudge, or I press a button, or do something to it to tell it to change state for a short amount of time, but then it automatically goes back to its stable state. In this case, zero, logic zero. A bistable needs a disturbance to change state every time. So there would be a disturbance here. There would be disturbance there, and there. So this is a timing diagram. So these are the logic levels, or voltage levels if you like, and this is time on the horizontal axis there. And a disturbance is required for a bistable multivibrator to change every time. An astable needs no disturbance. It will just keep changing on its own, and the time between each change is determined by the circuitry that makes up the astable. Okay? So quite often we use an astable to generate some sort of frequency if we need to. So music devices and all that sort of thing use an astable as part of their circuitry to control the frequency. So if you're producing, like say you've got a synthesizer, you press a note or a key on the keyboard and it produces a tone. Okay. Inside that circuit would be an astable, which is when you press that button, sets that frequency to produce the tone that you hear. Likewise, a computer clock. So you've heard about computers running at 2.4 gigahertz, say. Then there is a clock in the computer that is operating at 2.4 gigahertz. That will be generated by an astable. So an astable will be sitting there vibrating or flipping on and off at 2.4 billion times per second, so pretty quick. Okay, so all of these are a type of multivibrator. Now the bistable multivibrator is important to us because it needs a disturbance to make it to change state. And so if I were to have this circuit powered up and I set it to a particular state, it will stay there and remember that state for as long as the chip is powered up. And so that is a single bistable multivibrator effectively becomes 1 bit of memory. Now the type of circuit that we use to perform this function is called a flip-flop. So they're called flip-flops because they flip and they flop from one state to the other. Now there are several types of flip-flops and they all have different characteristics. They fall into 2 camps basically. You've got synchronous and asynchronous. So I'll start with the asynchronous. So the symbol for a flip-flop is usually just a rectangular box with inputs and outputs. Okay, so I'm going to have I'm looking at an SR asynchronous flip-flop at the moment. Okay, so that's this one. The SR asynchronous flip-flop has 2 inputs, S and R, and they are digital inputs, and 2 outputs. We call them Q and Q bar. Now, all flip-flops have 2 outputs, Q and Q bar, and what they are called is complementary outputs. Okay, complementary means that they are the same but opposite. Okay, so the same but opposite. Okay, and so you really can think of this as just being a single output, but internally you could kind of think of it like this. We've got Q here, there's our output Q, and not Q is just simply the Q but with an inverted Q. Okay? So you've got Q and not Q, or Q bar. So internally that's kind of how you can think of it. It's not how it's wired, but it's effectively how it behaves. And this is useful as well to have both complementary and to have complementary outputs, and I'll explain why when we look at counters. Okay, so the outputs on these are digital outputs and they are complementary. The inputs on here are digital inputs, and that there are 2 of them. So that means that we can control this thing with 2 signals. One of the best ways to show how the behaviour of a flip-flop is something called a truth table. So you look at the possible inputs and the outputs, and because we've got 2 possible inputs, we're going to have 2 times 2 possible input combinations, and so I need, which is 4, and so I'm going to need 4 rows in my truth table. Okay, so when both S and R are 0, so these are logic levels, logic 0, we get no change. Alright, so what that means is if Q is high, and by definition Q bar is low, then when S and R are 0, both 0, that just stays that way until we give it a disturbance. When S and R is 1 and 0 respectively, so basically what I'm doing is I'm setting the S pin, which stands for set by the way, it sets Q to be 1 and Q bar to be 0. Okay? So if it was already 1, then it doesn't change. But if it was 0, if Q was already 1, it doesn't change. But if Q was 0, it will set it to 1. And it will do that nearly immediately. Nearly, not quite straight away. There is a small delay, we'll talk about later. So that change happens very rapidly, like in the order of a few nanoseconds, but it is still noticeable delay, and it will set it to 1. And likewise, Q bar will go to 0. If I have set as 0 and reset, so set as 0, S as 0, R or reset to 1, that will set Q to 0, or reset it, and set Q bar to 1. So if set is high, then the output is high. If reset is high, the output is low. Okay? So when I talk about the output, I generally default into Q, because you can predict the operation of Q bar. Now there is one final possible state on input here where both set and reset are high. Now what's going to happen here is the set pin is trying to set Q high, and the reset pin is trying to set Q bar high, effectively. And so what it would try and do is set both of them to 1, but that can't be, because while one is high, the other cannot be high. So this is an illegal state. Okay, so they both you can't have both outputs high. So it's an illegal input. Okay. So that means that it is not allowed. You cannot have both S and R high. Now what would happen, you're asking, if I do put S and R high, is you get something called a race condition. Okay? So if S and R both 1, we get a race condition where effectively both Q and Q bar race each other, like a foot race kind of race. They're racing each other to be the first one to settle on being high. However, that means there's unpredictable, because we don't know. We can't predict whether Q or Q bar will win the race. And so it becomes an unpredictable state. And the whole idea of having digital circuits is that it is entirely predictable, and we don't want unpredictable events to happen in our circuits. So that's why it's illegal. Okay? So you could end up with Q being high or low, you just don't know. And it might change. It won't always be the same for the same flip-flop. It might change depending on temperature, depending on some other variables. And also, it'll probably also depend from flip-flop to flip-flop, things will be different as well. Okay? So generally we try and avoid that. And there are mechanisms in place that you can do to make that so that S and R can never be both high. Okay? Okay. Now, alright, so that's SR asynchronous. Pretty straightforward. The whole idea that S and R control what the output is fundamental to these types of flip-flops. Okay? For the synchronous, we have a third pin on input added. Okay? So I'm just going to rub off this to provide a bit more room. Okay, so for an asynchronous, we just have the two inputs, S and R, and the outputs. For a synchronous, synchronized means that the timing of them is synchronized, so that there's something controlling what time things happen. And in this circuit, it's called a clock. Okay? Now the clock pin, it controls when the outputs change. Okay, so the clock controls when the outputs change based on whether these two are high or low as well. So the truth table for the S and the R, controlling it, is the same, okay? So we still have, when S is high, Q goes high. When R is high, Q bar goes high. And you still cannot have both S and R high at the same time. However, the clock pin controls when that changes, okay? Now the best way to show that is with a timing diagram. So I'm going to draw a clock, and I'm going to draw it in a nice synchronised constant width just because it's neater and easier. However, it doesn't have to be. That clock signal could come from anything. It could come from a push button. So you can manually control the clock. Or it could come from some other circuit that controls the time. Okay? So I've got 3 clock pulses there. If I have, here's my S and my R, and I'm only, actually I'll not draw Q and Q bar, Q and Q bar. And so let's say that Q was low initially, and so Q bar is high. If I change set from being low to high, leaving reset low, okay? Now with the asynchronous circuit, what would happen is the output would change as soon as it saw this set pin go high, okay? So it's called level triggered flip-flop. So it triggers off the level of this logic on the input pin S. Okay? So for an asynchronous circuit, the output will change at the same time. So if I drew it there, you would see that happen. Okay? So this would be for asynchronous. However, with a synchronous, we have this clock pin, and it controls what time things happen. Okay, so it doesn't change until it sees, in this case, a rising edge. It sees the clock's input go from low to high, and that's what tells it, oh, now I can change. I can't change before then. And when it changes, that's when it looks at S and R and says, right, this is what I need to do. Okay, so when S and R are both low, when S and R are both low, we get no change. When S is high and R is low, it wants to set the output to high, and it will do that at just about the same time as the clock pin goes from low to high. Likewise, the Q bar goes from high to low. Okay. Now, importantly, I could have my set pin do this. And it wouldn't change. Okay? So my set pin can change, and my reset pin can do all sorts of stuff, including illegal conditions. So I could have that, and you can see we've got an illegal condition there. That's perfectly fine, because it's only until the clock edge is seen here, this rising clock edge, positive going edge, PGE for short. PGE is the positive going edge. It's only until that is seen that these S and R pins are even looked at. Okay, so at all this going on, if these were an asynchronous clock, flip-flop, we would see all sorts of problems, as well as it changing several times, potentially. We've got a legal condition there, so who knows what is going on. And so the output might be going up and down and doing all sorts of crazy stuff for an asynchronous, but with a synchronous, it's only until it sees this clock signal going from low to high that it would say, oh, yeah, okay, now let's look at the S and R pins. Okay. Likewise, if S goes back to 0 and R now goes high, it's not until the next rising clock edge would it change? Okay, so on the time that we see our next positive going edge there, that is when the output changes. So notice how my S and R, they changed at different times here. So that might be a factor. I could have made a completely illegal state for most of that time there if I wanted, or if it just happened to be. So let's add one in. Why not? Okay, that wouldn't have been a problem in a synchronous circuit. If it was an asynchronous circuit, we might be seeing all sorts of rapid changes on the output there. And if that was driving some other logic, that could cause further problems. Okay? So for a synchronous circuit, the outputs change synchronized by the clock pin. Okay? They're controlled by S and R, so how the outputs change, so what they change to is determined by S and R, but the timing that they change is determined by the clock. Okay? So we could say that the S and R pins determine what the output becomes. Okay, so underline what, and the clock determines when the outputs when the outputs change. So that's the main difference between the input pins and the clock pin. Pretty important difference. Okay, so an asynchronous circuit doesn't have a clock pin, and so the input pins determine both what they change to and when. Okay, now there are two different types. Actually, I'll look at the different types of clocks in a minute. Alrighty. Before I move on from S and R, has anybody got any questions about what the synchronous mean or anything like that? Alright. I have another video on my YouTube channel that I've done as well, and it's done, well, I think mostly the same, but there might be some differences. So feel free to watch that one as well. It might clear up some other matters as well. Okay, so S and R have more or less the same, depending on whether it's synchronous or asynchronous, depends on whether it has a clock pin, and depends on, what timing things happen. Okay. Now all of these flip-flops are made simply using AND gates. You do not need to know how they're made. You don't need to be able to draw how they're made. In your notes, I think you'll find a diagram that shows. Okay, now the next type of flip-flop is called a D-type. Now D-type is different than the SR type in that it has only got one input, and that fixes that whole problem about having an illegal input state. Okay? So you can't have an illegal input state when there's only one input. It's also got a clock input, so it is a synchronous circuit, and as with all flip-flops, it has the two outputs Q and Q bar. Side. Okay. So we have our input here, D, and we have our two outputs Q and Q bar. And effectively, the difference here is, unlike having a condition where the output, when the input is 0 with the SR, with both inputs was 0, the flip-flop didn't change. basically this one, the D logic level on D determines what the output is going to be after the next clock. So I ain't going to bother putting Q on this one because we all know what Q bar would look like, just the inverted version of it. Okay, so if D was low, and let's say Q was low, if D was low on the next rising clock edge, in this case, then Q stays low. Okay. If I change D to be high, then Q, after the next rising clock edge, goes high. Okay? And if I go back to low again, then you see we go back to low. So effectively, what you can think of as for the D-type flip-flop is D is the next Q. Okay? And the reason why it's called D input is because it's a delay or a data input. So the delay is, it delays the output here until the clock edge is seen from whatever that input is. So if I have my input changing from low to high, then it delays what the output does until the clock edge is seen. Okay? So that's quite useful. And it's also useful because it doesn't have that illegal input condition. And one other very useful way that we can wire this circuit is if I connect D to Q bar, have a think about what's going to happen here. So let's say Q is low, and I have, so Q bar must be high. Okay? If Q bar is high, then D must be high. So after the next clock pulse, Q becomes D, so Q goes from low to high. Okay, that's all good. But Q bar goes from high to low, so now we're back to 0. So now D is low. Next clock pulse, Q goes back to low again. Q bar goes high, so D goes high. And so every clock pulse, it toggles this circuit. Okay? And so I've kind of shown how that's done here. We've got a rising edge clock here. Actually, let's just have Q starting high. Make it a bit easier. So you've got a clock here. Sees a rising edge. The output changes. Okay? Yeah, the input the clock pin goes from high to low, then back to high again, and the output changes. Low, back to high again, the output changes. And so, if you have a look at how many pulses, or the time between these pulses here, so the time between the rising edges is the time that this thing is low. Okay? And by the time we've gone a full cycle, from high back to low and back to high again, it's twice that time. Okay?
Yeah. So basically you're just doubling the period.
Doubling the period or halving the frequency. Okay? Spot on. Okay? Very useful. Right, now I'll show you why this is useful in a later video, I think, or in a later lesson. So halving the period, doubling the period or halving the frequency is very, very useful. And it's very easily done with a D-type flip-flop. All you need to do is just connect two pins together. Okay. So that's D-type flip-flops. They are a synchronous flip-flop, meaning that the outputs only change when the clock rising edge is seen, or the appropriate clock edge. And the final main type of flip-flop that we're going to look at is called a JK type flip-flop. Now, JK type flip-flop is a bit like a mix between the SR type flip-flop, asynchronous, and the SR synchronous flip-flop. Okay? So we actually have 4 input pins on this one. Riley, next one. Okay, so we're going to have S and R. We're also going to have J and K. And the usual 2 upper pins. Now, the S and the R pins on this behave in the same way as the asynchronous S and R pin flip-flops do. Okay? So S and R, sorry, I should write, this is a JK flip-flop. Okay, so this is a JK type flip-flop. The S and the R pins behave okay, so the S and the R pins behave in the same way as an asynchronous SR flip-flop does. In that, if I set that pin high and have R low, so if S is high and R is low, then immediately, as soon as it sees, well, with a very tiny delay, as soon as it sees that S pin goes high, Q goes high. Okay, so if I have okay, so I don't care about what J and K are, so I'm just going to put a cross there. Okay, and instead of a timing diagram, we're going to use a truth table. Now, in this case, I'm showing that as being a rising edge there. So if I'm drawing an arrow going up, that means a rising edge. Draw the clock pin. Okay. In this case, I'm going to actually, sorry, that means don't care. And in this case, we're going to have Q, Q bar. Okay, so S and R, they don't care about the JK and the flip-flop and the clock pin because these are the asynchronous inputs. Okay. All right. Likewise, for these ones. So if R is 0, if S is 0 and R is 1, then Q goes to 0 and Q bar goes to 1. It doesn't care about the clock, J and the K inputs. And you cannot have that. So, not allowed. Okay, so both J and S and R cannot both be high. It's not allowed. And if S and R are both 0, then we can start looking at the other pins and see what they do. So if S and R is 0, J and K are 0, and we see a rising clock edge, we get no change. Okay? So if we see a rising clock edge here, that's really the only time this say right, sorry, I've just changed that a little bit. The clock edge, well, the clock can have anything. If S and R are 0, okay, well, now we're looking at the JK pins. If J and K are both 0, then well, it doesn't really matter what the clock's doing, we're getting no charge. Okay? It's only when we see a rising clock edge, S and R are both 0, and let's say J is 1 and K is 0, that sets the clock. So it sets the output on the timing of the clock edge to 1. Okay? So Q bar goes to 0. Okay? So this is the synchronous inputs here. Right, so my synchronous inputs here, J and K, they rely on having this clock edge, the appropriate clock edge be seen. Otherwise, it doesn't do anything. It doesn't change. Okay? If it sees anything other than a rising clock edge, no change. Okay, so that falls in this state here. Okay. Likewise, if we see a rising clock edge, S and R both 0, and J is 0 and K is 1, we see that. So this behaviour here is really no different than the synchronous SR flip-flop. So the synchronous SR flip-flop behaves the same as the J and the K inputs. This. Okay? Now there's one final difference between the JK flip-flop and the synchronous SR, and that is this state here where we have a rising clock edge, S and R are both 0, and J and K are both 1. Now this, when we had the SR synchronous flip-flop, the S and the R inputs couldn't both be 1 because that gives a race condition which gives an unpredictable output. So we couldn't actually determine what was going on. The JK flip-flop is wired slightly differently. What it does is it sets it to toggle mode. Okay, so toggle. Okay. So if Q was 1 on the already, and JK both set to 1 and it sees the clock edge, it'll change it to be whatever it wasn't before, so it'll make it toggle. So in the same way as when we wired up the D-type flip-flop to have D connected to Q bar, if we have both J and K set to 1, it makes it a toggle type flip-flop. Okay? So this is an important distinction between the JK flip-flop and any of the other types, in that it has a built-in toggle mode depending on what the logic level is. Okay? Okay, anybody got any questions about the JK type? Now we won't be working with JK types in our experiments. They aren't particularly commonly used because, well, they're big and bulky, and unless you need to have the functionality of the asynchronous and the synchronous inputs, it's kind of a bit of overkill. So quite often people, if they're just needing a flip-flop for like a counter or something, they stick with a D-type or something like that because they're cheaper and the chips are a bit smaller. Okay, now the final thing I want to cover here is the T-type. Now the T-type really isn't a particular, like you can't go out and buy a T-type flip-flop because they are made using either a JK type flip-flop or a D-type flip-flop.